Let's write some code to execute a rank 1 update. We begin our work by looking at the mathematical definition of a rank 1 update. In order to define a rank 1 update, we need to start with a matrix A in Rm by n, and then vectors x in Rm and y in Rn. A rank 1 update of A is given by A plus x times y transpose. This is also called an outer product update, since the matrix x times y transpose is an m by n matrix, the exact same dimensions of A, formed by taking the outer product between vector x and y. For more information about outer products, go ahead and see our previous videos on that topic. What we're going to do in this video is actually transform this mathematical definition into code that executes that calculation. Let's go ahead and start with a blank script file, and we'll save it in our BLAS level 2 sandbox file. So this is going to be a rank 1 update via columns sandbox. All right. Let's start with m equal to 3, and then we'll also set n equal to 3. We'll do a square matrix in this situation. We'll say that A is going to be, instead of doing a random integer matrix, let's just call it a random, pseudo-random number between 0 and 1. You can help rand if you want to see more about that. X will do the same thing. This is going to be a random vector with m rows and 1 column. And then the same thing is true for y. So y is going to be a random vector, pseudo-random vector with n rows and 1 column. Then what we're going to say is that MATLAB's version of this, so let's call it BMAT, is going to be A plus x times y transpose. And that's going to be what we call a rank 1 update. So if we run this, BMAT, that's the output. It's kind of hard to see that. This is why it's kind of nice sometimes to do random integer data, because you can actually do the calculations for yourself. We've done that a lot in these examples, so I'm going to actually kind of branch out a little bit. In this video, what we're going to do is create our own algorithms for this. And we'll start with a BLAS level 2, so vector data, and we'll do a column partition. So let's go ahead and define a new matrix B with all zeros. Again, we are not worried about the memory efficiency at this moment. We're just testing ideas. So if we think about the size of this, and we're going to go over the columns, we must go from k goes from 1 to n, since there are n columns. And we're going to say that the kth column of the desired output is going to be the kth column of A. And then let's think about what this outer product is. Remember that the outer product is formed in one of two ways. One way to think about it is to take the kth entry of y multiplied by x to form the kth column of the outer product. The other version is the row version, the ith entry of x multiplied by y transpose to get the ith row. In this case, we're doing it by columns, so we might say this is going to be the kth entry of y multiplied by x added to the kth column of A, and then store that in the kth column of our desired output. Let's go ahead and look at the error between the matrix that we produce and the matrix that MATLAB produces. That error will be exactly 0 if our algorithms run the exact same way. So let's look at error. Oh my God, it is exactly 0. I was not expecting that. Now that we know that we have a working algorithm, let's do a little bit of finagling, some changes to improve the memory features of this. Specifically, instead of using a new matrix B to store the rank 1 update, let's just override the previous matrix A with the new rank 1 update, meaning that we're not going to have new data in memory. We're reusing old memory locations for the update that we desire. If we do that, after we exit this loop, the matrix A will now store the desired rank 1 update, and we can look at the difference between the two of them. Let's go ahead and look that our error is 0. Indeed it is. And now we're ready to do a little bit of analysis of what's happening in this work. The mathematical operation that we're doing is a rank 1 update A plus x times y transpose. We're doing this by columns, so we write a for loop that runs over the columns. K goes from 1 to n. Then we update the kth column of A with the previous kth column plus the scalar yk, the kth entry of y, multiplied by the column vector x. Notice that each one of these individual updates in the body of this for loop is an AXB operation with column vectors. Remember, AXB is scalar alpha times vector x plus vector y. So scalar times vector plus vector. We've seen this multiple times throughout our algorithm development, and that's exactly what we're doing with this rank 1 update. We're doing a column Saxby in each iteration, which means we might replace that with a for loop. We're not ready for that yet. Let's analyze this column partition version to see what's happening. When we initialize our algorithm, we have a matrix A sitting in memory, and then we have two vectors, x and y. In our case, we stored those as column vectors. I'm visualizing y as a row vector since I am using the transpose to form the outer product. But this is just to make the visual a little bit more appealing. In reality, if it's stored as a column vector in memory, we can still do this algorithm, which is exactly what we saw. Once we initialize that data in memory, we move into the for loop. So we set the loop index equal to 1, which means that we start with the first column. The first column of the outer product is going to be the first column of A plus y1 times the entire vector x, and that's exactly what we see here. Then we update our loop index. So now we go to the second column of A. We add that to y2 times the vector x. Then we go to the third column and add the third column of A with y3 times the entire vector x. After we've completed our loops, we exit, and the matrix A now stores the rank 1 update that we wanted to calculate. Now, I know you all have super sharp minds. This AXB operation here, this column AXB operation, of course, could be replaced by the corresponding for loop. In other words, we can drop from BLAS level 2 down to BLAS level 1. So instead of doing vector information, we could do scalar information. Let's go ahead and just copy, paste, and then we'll comment this one out. So there we go. And then here what we're going to do is replace the body of this loop with another for loop that runs over the rows. So I goes from 1 to m, and we'll end this one. And then we're going to say that the ikth entry of A is going to be the previous ikth entry, so aik, plus well, let's see. This is going to be the kth entry of y times the ith entry of x. And then, of course, we should test this to make sure that the algorithm is working as we desire. The error between the two of those is 0. So we say that our algorithm is producing exactly what MATLAB does. Let's visualize what we've done. Here again, we're doing a rank 1 update operation, which is A plus X times Y transpose. We're doing this using a doubly nested loop where the new value in row I, column K of A is the old value in that position plus YK times XI. When we initialize this algorithm, we store A in memory, then we store X and Y in memory. Let's drop into the for loops. We'll do the outer loop first. So we set K equal to 1, which means we're in the first column. When we set I equal to 1, we're in the first row of that column, and we take the previous value of A, we add that to Y1 times X1, then we increment the inner loop. So now we go down to the next X2, Y1 times X2 plus A21, go down to the next one, A31 times Y1 X3. That gets us our entire first column, which means we increment our outer loop, which goes up to column 2. We take the previous value, add that to Y2 times X1, Y2 times X2, Y2 times X3. Now we increment our outer loop index, and we go down to the third column. We add the previous value to Y3 times X1, take the one below that, Y3 times X2, Y3 times X3, and when we exit our loops, A now stores the rank 1 update that we desire. That leads really nicely into the community challenge for this video. Both algorithms that we worked on to implement a rank 1 update did so using column AXBs. In other words, scalar A times vector X plus vector Y. How would you change this algorithm to do a row partition version? So to use row AXBs instead. What changes would you have to make to the BLAS level 2 and BLAS level 1 approach to process by rows? Go ahead and implement those for yourself, and of course develop a visualization to describe what's happening in the flow of your algorithm. Yet a second challenge for this video is, now that we've seen what a rank 1 update is, can you begin to craft some program specifications to actually turn this rank 1 update algorithm into a function file that we can put into a library? go ahead and look back at the previous function files that we've implemented as part of our library, and that should give you some inspiration on where to get started in your thinking. One of the challenges for this lesson is to code up your own function to do a rank 1 update in the form a plus scalar alpha times vector x times y transpose. Go ahead and form the specification list using the structure that we've done previously. Title your function d sub GER. So this is going to be a double general matrix rank 1 update. That's what's going on there. Do all the error checks, make sure it's all working just like we've done before, and then add that to your library. Look, you're building your matrix functionality out in your own personal library. Pretty exciting. Thank you so much for your attention. In the next lesson, we're going to go on to matrix multiplication. Super excited. I'll see you there.